Okay, well, thank you for the opportunity to talk in this conference. I'm from Universidad de Valparaíso, and I will show my results of my thesis work in the wide dwarf binary pathway survey. This survey is dedicated to the study of the binary stars or post-common envelope binary stars with intermediate mass secondary star, and the aim is to study the evolution and try to constrain some of the parameters that the evolve. And the mass transfer will cover the entire binary in a common envelope. When this common envelope is ejected from the binary, we'll take angular momentum with it, and will result in a closer binary with the core of the Volbet star now being a white dwarf. What will happen next will depend mainly on the orbital period of this binary. And for long orbital periods, the secondary star will have the chance to evolve into a second common envelope and produce a double white dwarf, and these possible outcomes. For short orbital periods, and depending on the mass ratio, they can experiment a stellar merge, or can be a super soft source and maybe produce a supernovae, or evolve into a cataclysmic variable. And in order to cover most of these possible evolutions, we are studying these binaries with secondaries of the spectral type A, F, G, and K. Observing these binaries is not easily as it can be thing, because the secondary completely outshines the white dwarf in the optical. So to overcome this problem, we combine optical with ultraviolet observations, and we selected all those F, G, and K stars that show an extra emission in ultraviolet, and they are shown here in blue with the blue dots. I observed this nearly 500 of this system, of this candidates, and by selecting those that show radial velocity variations, I continue observing them and to calculate their orbital period. And from those systems that I found the orbital period, I selected these 5 stars shown in red. Here is the mainly I select these stars because they are very similar between each other. All of them have G-type secondary stars, except this one that have a K secondary star. And by doing spectral fitting with spectral models, we find their parameters and found that the secondary star in these 3 systems, it's a bit evolved. This is the radio of the secondary, is a bit larger than it should be in the 0 and H main sequence. And also with other study, we found that this system is a triple, hierarchical triple system, in which the inner binary is the post-common envelope binary. all the orbital periods of these binaries is between 20 hours and 2.5 days. And also for these two systems, I observed with tests, or I get the test observations and studied the light curve. The photometrical signal of these light curves match very well with the orbital period, and we conclude they are tidally located. And we found that the secondary stars in these two systems are very active. They show flare activity and also star spots. And the star spots in these two systems is different between them. And this system, the star spots are changing over the different epochs. I mean, they are appearing and disappearing and changing their position. And in this other secondary star, the star spot is always the same, but they are migrating in the surface of the secondary star. And also by this moving, and also this moving movement in the surface of the secondary, we can find that this star is differentially rotating. Also, for this star, for this binary, I obtained HSD observations and can confirm the presence of the white dwarf, and confirming that our target selection is efficient. And we calculate their mass, and also could see or observe their emission lines that they are usual to see in systems that are transferring mass. And we observe with X-rays, and we couldn't confirm any mass transfer, so we conclude the emission lines are produced by the activity of the secondary star. With the parameters I found of all these systems, I performed MESA simulations to predict their future. And for two of those systems that also have their radio is a bit expanded, or the secondary is a bit evolved, they will run into dynamical unstable mass transfer, show it here with the blue dots. And the energy will not be enough, and they will merge into a single star and eventually into a single white dwarf. There are other two secondary stars. No, there are other two binaries, I mean, showed here in red, and they will evolve into a cataclysmic variable with evolved secondary stars as well. This means the mass transfer will not stop during even during the period gap. And the other system have many possibilities to be a super subsource. But this means the white dwarf will increase its mass, but will not reach the Chandrasekhar limit and will not explode into a supernova 1A. Also, with this study, I did this orbital period distribution and found that there are two populations of post-common envelope binaries with massive secondaries. Here in this figure, I showed post-common envelope binaries with M dwarf stars or M dwarf secondaries, and they always well, less massive, and their orbital period is never longer than 10 days. And
2 minutes.
Yeah,
2 minutes,
and for the
please.
more massive secondaries, we can see two populations: one with short orbital periods, and other with long orbital periods. And making a comparison with the population models, we can see that the short orbital period systems fits very well with the with the theory or the hypothesis that the common envelope needs fixed energy alpha, or percentage of energy to bind the common envelope, while for the binaries with longer orbital periods, they need some extra energy. Or maybe that exists the possibility that these long orbital period binaries skipped the common envelope and experiment stable non-conservative mass transfer to reach the shorter orbital periods. And in this way, we can found a bigger populations of double white dwarf binaries, and this can have a bigger impact in the supernova 1A production. And I will let my conclusions here, and we'll be happy to receive any questions you have.
Thank you for finishing exactly on time. Noam has a question.
No, I don't.
Oh. Well, does anyone have a question? Rudy.
Hi, Stephania. That was a really excellent talk. Can you hear me?
Yes, I can.
So you mentioned that you looked for X-rays and didn't see any sign of X-rays and activity from that. But I wonder if you looked at the companions, the AFGKs, to look for abundance anomalies that may have come from a past mass transfer event.
You mean if this is this activity is produced by the past common envelope?
Right. If you saw some unusual abundances that were not that did not agree with the standard set of abundances for a star of this metallicity in certain elements that would have been liberated during the post-common envelope from the white dwarf.
Well, we didn't consider that actually. It could be possible maybe in the case of this binary, because this system also show X-ray emission, but we couldn't confirm it's due or it's produced by the mass transfer. Maybe it can be, but the activity is actually really strong in these two systems, and we thought that maybe this emissions it's produced by the flare activity.
Right.
And winds, actually.
Very nice work. Thanks.
Thank you.
Rob, you want to ask your question?
Yeah, well, beautiful talk. Really impressed by the data. So quick question, has anybody tried to look for the planetary nebula which had to be ejected and formed around these white dwarfs at some earlier stage of evolution, or these are just too old and the PN has long been dispersed, so there's no hope of detecting it?
No, we didn't try it, but I know about one system that one of my colleagues is studying, and they have one system that probably that they thought that they have they are observing the common envelope, but in these systems I am showing here, we are not trying to observe the past.
Well, I understand it. My question is, would you expect that there's a possibility that some of these systems you might be able to see a planetary nebula with some very deep imaging, for example, or they're just so old that it's impossible?
What are the temperatures of the white dwarfs? I mean, they're all pretty old white dwarfs, aren't they?
In these ones, they was between 10,000 and 10 and 20,000 kelvins.
So those are
Yeah.
those are pretty old. So that any planetary nebula is long gone, I would think.
Right. That's what I thought was. Maybe I was wondering, maybe there are systems which might be a little bit hotter, the white dwarf, so there might be a chance. But okay,
Yeah.
if your temperatures are so low, then probably the chance of seeing a planetary nebula is impossible. Thank you.
Yeah. Thank you.
Now, none of these systems show eclipses, do they?
These systems, no, but I think
Yeah.
I have one that shows. I have not deeply, well, I have not studied deeply yet, but I think there is one that shows
Oh,
eclipses.
that would be wonderful.
Yeah.
Rob, there's a question?
Hi, thanks for this. It was really great. Let me see if I can get the video working. It's very dark here now. I don't know why. Weird. And I was just wondering, is this data available somewhere in a database that the rest of us can use?
I'm sorry?
Is this data available in some big database that I can download to constrain our models as well? Or is it still?
No, but in the papers I made available the radial velocities, and well, they are the names, and you can download the test data and everything.
Okay, thank you.
Yeah.
Okay, I don't see any more questions, and it's time to take our 10-minute break. So we'll resume at 17 hours GMT.